Hello, my name is Hugo Aramberri, and I would first like to thank the organizers for giving me the opportunity to present our findings. Now, the work here presented was carried out at the Luxembourg Institute of Science and Technology under supervision of Jorge Iñiguez and together with our collaborators in Barcelona, Max Stengel and Claudio Cazorla. The funds come from the Fonds National de la Recherche of Luxembourg, and in this work we asked ourselves, is lead zirconet really an antiferroelectric? Let me give you a brief introduction to this compound. Now, lead zirconet is considered the prototypical antiferroelectric perovskite. Its structure features an antipolar mode that involves antiparallel displacements of the lead atoms so that they follow a down-down-up-up pattern, as you can see here to the left. Now, the structure also features an antiferrodistortive mode, which you can see here in the center, corresponding to the oxygen octahedra tilting following an A-A-C0 pattern in Glasser notation. Now, overall, the full optimized structure, which you can see on the right, contains 40 atoms per unit cell and is known as the ground state of lead zirconet. Now, we will label this structure as AFE40 for the rest of the talk. The motivation for this study came from several hints in the literature pointing at low energy states of lead zirconet with uncompensated dipoles. Now, here on the left, you can see a recent work in which a ferroelectric state was stabilized in lead zirconet with doping. Now, in the center, you can see an experimental work reporting on polar domain boundaries in this compound, and on the right, you can find a field-induced ferroelectric phase that was experimentally stabilized in pure lead zirconet. So we decided ourselves to build a simple ferroelectric phase and study it using first principles. Now, to do so, we set the lead displacements to follow a down-down-up displacement pattern, as shown here in the figure to the right. Now, this dipole structure would be ferroelectric by construction. On top of that, we condensed the leading instability of this compound, the one at the R point, so that the oxygen octahedra tilts follow the A-A-C0 tilt pattern. Now, the question now is this structure stable? So we optimized this structure using density functional theory, and we found out that indeed this ferroelectric polymorph of lead zirconet is stable. Not only that, but we find that this phase, which we label FIE for ferroelectric, displays an in-plane polarization of 0.11 coulombs per meter square, and that the displacements of the lead atoms are very similar to those of the antiferroelectric phase. Now, the oxygen octahedra do follow the A-A-C0 pattern with minor distortions, and overall the structure belongs to symmetry group IMA2. We further analyzed the mode decomposition of this phase using standard crystallographic tools. So we found that the strongest distortion is the one shown here on the left, which has R4 plus symmetry, and this mode accounts for 53% of the total distortion and is the one giving the A-A-C0 tilt pattern of the oxygen octahedra. Now, the second most important distortion is the one in the center with sigma-2 symmetry, and accounts for 34% of the total distortion and features antipolar lead displacements with a 2 down, 1 up modulation. And we also find a gamma point mode accounting for 9% of the total distortion that is responsible for the onset of a net polarization, and we find two more minor modes that I am not showing here. Now, in order to carry out a phase stability study, on top of the AFE40 and the ferroelectric phases, we included two more phases in the mix. So first, we include in the comparison a simple ferroelectric phase, which we label FE, that you can see here on the bottom left. This phase has R3C symmetry and has the same structure as, for instance, the ground state of bismuth ferrite, with the polarization lying along the 1-1-1 direction. Now, the one here on the bottom right, which we call AFE80, corresponds to the condensation of a small instability that we found in the AFE40 phase, which I will now play for you. Okay, so this cell-doubling instability involves the antipolar displacements of the lead atoms along the Z direction and some minor distortions of the oxygen octahedral tilt pattern. Now, let me note that although we found this structure independently, this phase was predicted by Baker and collaborators while we were running the calculations. The first thing we compared were the energies obtained with density functional theory of the four polymorphs. So using the PbZrO3 exchange correlation functional, we find the results displayed in this table, where the energies are in milli-electron volts per formula unit, and they are all relative to the AFE40 phase. So first of all, we see that all the polymorphs lie within a 1 milli-electron volt per formula unit window, with tiny energy differences among them. We see that the AFE80 shows the lowest energy, very closely followed by the ferroelectric state, then by the AFE40, and finally by the ferroelectric phase. So let me point out here that we found very similar trends in the closely related compound lead hafnate. The next thing we studied are the phonons of the four phases. Now you can see here that all of them show no instabilities, except for that one at the set point of the AFE40 phase. But as I mentioned before, it is precisely the condensation of this instability that leads to the AFE80 phase to its right. Now overall, we find that all the phonons of the four phases are quite similar, and importantly, the phonons show that the new phases, namely the ferroelectric and the AFE80, are both dynamically stable. So once we have computed the phonons, we can now use them to compute the zero-point energies. Now, the zero-point energy of a solid is nothing but the vibrational energy of the system at zero temperature. This term is often not considered because it's relatively expensive to compute, and its effect is usually small in the relative phase stability. But having found such tiny energy differences among the lead circulant phases, it is justified to compute it in our case. Alright, so here we can have a look at the DFT plus zero-point energies of the four lead circulant phases with PbZrO3, and we find the following. So although the differences among zero-point energies are small, as expected, they are enough to revert the relative phase stability between the ferroelectric and the AFE80 phases, so that the ferroelectric state becomes now the one with the lowest energy. Now, we can study how the free energies evolve with temperature within the so-called harmonic approximation, for which we also need to perform sums over phonon frequencies, as you can see in the formula here. Now, the results for PbZrO3 are shown in the figure, where we plot the free energy differences to the AFE40 phase as a function of temperature. We see that the ferroelectric state is the most stable at low temperatures, up to around 250 Kelvin, although our calculations do not allow for a great accuracy for this value, as you will see. Then, the AFE40 phase becomes the most stable, up to at least 500 Kelvin. Now, notably, the AFE80 phase is never the most stable phase among those studied here. We completed this study with three other exchange correlation functionals, namely LDA, PBE, and SCAN. We found that LDA yields the same qualitative behavior as PbZrO3, but with a larger critical temperature of 460 Kelvin. Now, on the other hand, the results with PBE and SCAN are not compatible with the experimental evidence we have for lead zirconet and can therefore be ruled out. Now, unfortunately, I do not have time to discuss this point in the present talk, but you can follow the discussion in the publication we did on this work. As a final sanity check, we computed the effect of the thermal expansion within the so-called quasi-harmonic approximation. Now, because these calculations are very demanding, we only did so within PbZrO3, and we only did so for the ferroelectric and antiferroelectric 40 phases. So here you can see the results for the Gibbs free energy differences of the ferroelectric and AFE40 phases as a function of temperature. Now, overall, we find that the behavior is qualitatively the same, but we also see that the critical temperature has risen to 360 Kelvin, indicating that our results are qualitatively robust against the effect of thermal expansion. Okay, so let me stop briefly to make an important point. Our first principles calculations predict that lead zirconate is ferroelectric at low temperatures. Then, at a finite temperature, which depending on the calculation details is somewhere between 250 and 460 Kelvin, the usual antiferroelectric phase becomes the most stable. Now, these results have been checked against the choice of exchange correlation and thermal expansion and seem robust. Alright, so having found this, the main question we had is, can we reconcile our predictions with the experimental knowledge of lead zirconate? And we believe that that is the case. So experimentally, lead zirconate is always prepared at high temperatures of the order of 900 Kelvin, well inside the cubic phase. And then, upon cooling, the AFE40 phase is condensed at a temperature of around 505 Kelvin. So in order to reach the ferroelectric phase we propose, the system would have to first be cooled down below the critical point between the AFE40 and ferroelectric phases, which could be below room temperature and therefore not usually explored. And second, and very importantly, the system has to overcome the energy barrier between these two phases. So it is therefore possible that the transition to the ferroelectric state is kinetically hindered, and that could explain why it has not been noticed yet. Now finally, we asked ourselves the following question. Has the ferroelectric phase already been obtained? Now in this slide, I am showing 4 experimental works reporting PE loops of thin films of lead zirconate with non-zero remnant polarizations, and in some cases even with a central bubble that is compatible with ferroelectric behavior. Now the reported remnant polarizations are close to 0.10 coulombs per meter square, which is quite close to the computed spontaneous polarization of the ferroelectric phase. So overall, this means that the ferroelectric state may have been already stabilized, but not recognized as such. So with this, I come to my final slide with a brief summary and some conclusions. First and most importantly, we have found out that lead zirconate is not antiferroelectric at low temperatures. The ferroelectric phase is instead the most stable, and it could even be the most stable at ambient conditions. Now, admittedly, we have only tried one simple ferroelectric phase, and it's possible that other ferroelectric phases with different dipole modulations further lower the energy. The question of how to develop accurate effective models remains not completely solved, and this new phase should probably be taken into account in future models. So finally, let me say that this work has been published in NPJ Computational Materials last year, and you can find out more details about it in the reference shown at the bottom of this slide. Thank you for your attention.